In this video, we're going to use trigonometry to come up with or derive a formula for the area of a triangle that only uses the side lengths and the angle measures. In addition, we're going to use that area formula to come up with a property called the law of sines, which is going to be useful for us for solving triangles that are not right triangles. Up to this point, we've only been able to really work with right triangles because trigonometry only works on right triangles, sine, cosine, and tangent. But we're going to find a technique that'll let us divide up any triangles into right triangles so that we can use some of these trig functions to solve, in some clever ways, to solve triangles completely. We'll start with this area formula. We already know that the area of a triangle is 1/2 base times height. 1/2 base times the height. The thing is, the base can be any side of this triangle, but the height has to be an altitude. It has to be measured at a right angle. So unless you have a right triangle, which has two sides that are perpendicular, or you already have an altitude drawn in, it's not intuitive how to find what the height of a triangle happens to be. However, we can use trig to find it, to find a representation of what the height should be. So here's a triangle, and I've labeled the triangle, the angles as capital letters A, B, and C. And the convention is the sides that are across from those angles are the lowercase version. So the opposite from angle A is lowercase a, opposite of angle B is lowercase b, and opposite of angle C is lowercase c. If I want to find the area of this triangle, I need to choose a side to be a base, and I need then to draw and somehow construct or derive what the height needs to be. I'm going to start with I'll use the base that's on the bottom, just because, well, it's on the bottom. But I'll also, in a minute, show you how this applies to any other sides. If I say this bottom side is the base, that means an altitude has to come from this angle that's across from it, and we'll come down and hit this side at a right angle. And by doing this, this divides this triangle into two right triangles. So if I want to come up with an expression for what this height should be, I should be able to use trigonometry right now because I have two right triangles. So I could look at it from either side of this triangle. From angle A's perspective, I have the height of this right triangle. And the one side that I actually know that I have a name for the full length of, I don't know what this full length is because it's part of this side, so I don't really want to deal with that. But I do know that the side we're calling little c is the hypotenuse of this half of this smaller right triangle. So I am looking for the height, which is opposite of A. I know the hypotenuse of this right triangle. That's h. So I know O and H in SOHCAHTOA for this right triangle. I think I know that the sine of angle A is equal to this height over this hypotenuse of this right triangle. Or better yet, if I cross multiply, I find that the height is equal to C times the sine of A. So if I wanted to write down the area of this triangle, the area of this triangle is 1/2 base times height. That's 1/2. The base, the symbol I'm using for that is little b, is the base. And the height is h, but we know a formula for h. That's C times the sine of angle A. I didn't need to use this left triangle. I could have looked at it from the perspective of the other angle. Like I could have still had this altitude, but I could have done it from angle C's perspective. Because here's also a right triangle. I still don't know what this little part is, but now I know that from angle C's perspective, from angle C, so if I did this with, say, sine, if I did sine C now, then the sine is opposite over hypotenuse, so h now over little a. or this is the height now when I cross multiply is little a times sine of c. So another way to write the area might have been 1/2 of the base, which is still b, but now the height is a times sine c. Two different area formulas for the same triangle. Now note I didn't need to even use b as the base. I could have said that maybe side A is the base, and I drew in an altitude here and perform the same idea. Now this altitude is the height. If you continue doing this, what this boils down to is that you always get a formula of something similar to this, where you have a half, you have two sides multiplied together, and an angle. And it turns out, if you look closely, that these three letters are all different, and more so that in this case of this, B and C are here, B and C are here, and the angle is this angle that's included in between them. Or, if from the other perspective, B and A, and the angle is the angle is C. It's the angle that's included in between them. So in general, when you do this, you end up with this pattern, is that the area of a triangle is 1/2 times a side times the sine of the included area, or included angle. And by included, I mean the angle that's in between any two sides you choose. So to find the area of a triangle, you don't need to find an altitude. You don't need to draw in any any perpendicular lines. You don't need any of that stuff. All you need to do is know two sides of your triangle and the angle that's included in between those two. And if you can do that, then you'll know the area of your triangle. What's nice is that we can apply this idea in a pretty clever way to find a way to relate the sides and angles of any triangle, whether they're right angles or not. So what I'm going to do is I'm going to write there are actually three distinct ways to write the area of this triangle ABC. Which all come from picking the angle to the perspective of the angle to look from. So for instance, if I look from angle A's perspective, the area of this triangle would be 1/2 from angle A's perspective would be side B times side C times the sine of angle A. If I look at it from a different angle's perspective and I write the area formula down, it should still have the same area. So how about instead, if I look from angle B's perspective, then if I use angle B in here, then I need a 1/2, and then the two sides that angle B is included between are A and C. And lastly, from angle C's perspective, this again is the same triangle, so it should have the same area from angle C's perspective. Then the sides that are included, that C is included between are A and B. So since these three area formulas are three different ways to represent the area of the same triangle, they ought to be equal to each other. Some algebra I can do with this. I know that they all have a half, so if I multiply each of these by 2, then I'll cancel out this half. It's like if I do the same thing to every equation, then I keep the equations balanced. Also, I can divide if I divide expressions by the same thing, they'll still be in the same relation. So I'm going to divide by this clever number, and the number is the number you get when you multiply all three sides together, A times B times C. Note, since this is a triangle, it can't be 0, so this is fair game. So I'm going to divide everything by the product of the sides, A times B times C. A times B times C. A times B times C. And when you do this, we end up doing one of my favorite things to do in math, which is canceling and reducing fractions, because I see some things alike on top and bottom. B and B are alike on top and bottom, so I don't need them anymore. C and C are alike on top and bottom, so I don't need them anymore. And what we end up with is this first fraction simplifies. The only thing left is a sine A on top. and a little a on bottom. In the middle one, a cancels with a, c cancels with c, and the only thing you're left with is this ratio sine b over little b. And unsurprisingly, a cancels with a, b cancels with b, and the only thing left in this third ratio is sine c over c. This relationship is called the law of sines. What this tells us is that for any triangle, it does not matter whether it's right triangle or not, for any triangle, the ratio of the sine of an angle compared to its opposite side is always the same. So in practice, what we're going to do to use this law of sines is we're going to find a ratio and another ratio. Hopefully we'll know 3 of the 4 things in this ratio, say both angles and one of the missing sides, or 2 sides and one of the angles. We'll set this proportion equal to each other, and then we'll cross multiply and get the missing thing by itself. Again, this is really important and really nice because this works for any triangle, right triangle or not. And this works for any triangle because we came up with it. This is derived from the area of any triangle, right triangle or not. So the area of a triangle and the law of sines are very closely related, and they're both very useful formulas that we're gonna see going forward.